Good afternoon, class. Here's exam 4 review, chapter 4, application of differentiation, chapter 5, integral, 6.1 areas between curves, and here's the second part, 4.9, antiderivatives, 5.1 areas and distances. Anti-differentiation. So, as the name indicates, is the reverse process of differentiation, also known as integration. So let's look at some of the basic differentiation formulas. For example, the derivative of k times x is k, where k is a number, is a constant. Therefore, the integral of k dx must be kx plus c, the reverse process. The derivative of x to the power of n, this is called the power rule, is nx to the power of n minus 1. The integral of that must be x to the power of n plus 1 over n plus 1 plus a constant, and n can't be negative 1. I want to go over this with a couple of different methodologies. Number one, let's look at the process that takes place for differentiation for the power rule. So when you want to differentiate x to the power of n first, you have to multiply by n and then subtract 1 from n. So you multiply by n and then you take away 1 from the exponent. The integration must be the reverse process. Reverse process means go this way. So this becomes number 1. Subtraction means addition. Add 1 to n. Number 2, multiplication becomes division. Divide by n plus 1. So that would be one justification. The other way that I'm going to justify that, if we differentiate this, so let's call this capital F of x, equals 1 over n plus 1. This is another way of writing it. X to the power of n plus 1 plus a constant. Let's differentiate this. Differentiate this. We get 1 over n plus 1 times n plus 1, x to the power of n plus 1 minus 1, and a constant gives you 0. These two cancel each other, and this is x to the power. In other words, that's a proof that the integral of x to the power of n is 1 over n plus 1, x to the power of n plus 1, and a constant. Let's look at others. Let's look at some functions that we have differentiated already. If the derivative of e to the power of x is e to the power of x, then it's integral. The by integration means integral of e to the power of x dx is also itself and a constant. By the way, speaking of a constant, I want to make sure we understand the reason we add a c a number, because the derivative of a constant is 0. So the result is a family of functions. When you differentiate, you get one function. When you integrate, you get an infinitely many different functions. If the derivative of natural log is 1 over x, then the integral of 1 over x must be a natural log, and of course a constant. So we write it in this fashion. By the way, 1 over x or x to the power minus 1 means the same, natural log of absolute value of x plus c. As far as absolute value is concerned, class, as you know, the domain for natural log is from 0 to infinity. And 0 is not included. That's why we put in an absolute value. If the derivative of sine is cosine, then the integral of cosine x dx must be sine and a constant. By the way, you need the dx, and I'm going to write this for you, class. Remember, for example, if y equals f of x, then y, and then f prime of x or dy dx are the same, and dy is f prime of x dx, and we need the dx because it in essence gives us the independent variable. All right. Cosine, the derivative is negative sine. So the integral of negative sine is cosine, but we're not going to put negative. We're going to put the negative on the other side. So the integral of sine x dx must be minus cosine x plus a constant. Let's look at trigonometric functions. If the derivative of tan x is secant squared, the integral of secant squared x dx must be tan x and a constant. cotangent, the derivative is negative cosecant squared. So the integral of cosecant squared x dx, remember we're going to have this, okay, would be minus cotangent x and a constant. The derivative of secant is secant tan, so the integral of secant x tan x dx must be secant x and a constant. If the derivative of cosecant is negative cosecant cotangent, the integral of cosecant cotangent must be minus cosecant x plus a constant. So believe it or not, that's the justification. Also, as far as the constant, as you recall, we do the same thing with the differentiation. If there's a constant, just keep that constant. You can put it outside the integral sign, inside makes no difference. The sum and difference rules mention the same thing again with the differentiation. You differentiate term by term. Also, you integrate in the same manner. Finally, what I want to mention is the derivative of e to the power of kx is itself times k. So the integral must be itself divided by k, the reverse process. And if you have any doubts, if you differentiate the final result, you get this one without the dx. So that's anti-differentiation, also known as integration. So find all functions g such that g prime is 4 sine x plus 2x to the power of 5 minus square root of x over x. So you want to anti-differentiate this. You are looking for a function whose derivative is g prime. That's the idea. So what is the process? Sometimes you will need to simplify first, factor, cancel, remove radical notation, etc. Sometimes you will need to integrate using substitution. So there are different methodologies. So for example, right here, first we cut this into two fractions. This is cut into two fractions. So this is 4 sine x. This is 2x to the power of 4. This one we change it to x to the power of 1/2. And according to the quotient rule, x to the power of 1/2 minus, remember this one, when we don't write the exponent, is 1. So minus x to the power of 1/2 minus 1, which makes it negative 1/2. Now it's ready to be integrated. So you want to integrate this. And of course, times dx, you put this. This is an elongated s. We're going to discuss that further and later. Leibniz used that this because refers to summation as far as integration is concerned. So we want to integrate this. We're going to do it one by one. And again, put this here in case you want it. The derivative of sine is cosine, but the integral is negative cosine. So this is negative 4 cosine x. This one, we use the power rule. So you add 1 to the exponent, becomes 5, 2 over 5 x to the power of 5. And this one, you do the same thing, minus. You add 1 to the exponent, okay, negative 1/2 plus 1, and divide by it. So notice minus 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1. And at the end, in one shot, you add just some number. We call it plus c. Now, all we have to do is simplify this one. This is 1/2. 1 over 1/2 is 2. And as you know, x to the power of 1/2 is square root of x. So this would be the final answer, everybody. All right. We want to integrate this. We're going to do it term by term, starting with the first one. First, 2 divided by 5, you add 1 to the exponent. 2 over 5 x to the power of 5. This one, we add 1, we get 4. So 3 over 4 x to the power of 4. This one, we add 1, becomes 3 minus 7/3 x cubed. Again, reminding everyone when the exponent is not there, means x to the power of 1. So add 1, divide by it, 1/2 x squared minus 5 x plus a constant, and we're done. What about x minus 5 quantity squared? Reminding everybody that a minus b quantity squared is a squared minus 2ab plus b squared. Therefore, this is x squared minus 10x plus 25. I'm assuming everybody is comfortable with that. So this becomes 1/3 x cubed. What about this one? This one, just like this one, has the exponent 1, negative 10 divided by 2. Minus 5x squared plus 25x and a constant. And we're done. These are exponentials. And remember, for the differentiation, you multiply by k. For integration, you divide. So the answer is itself, but since it's integration, we divide by 4 and a constant. So this is 1/4 e to the power 4x plus a constant. This one, it's itself, but divided by -3. That means negative 1/3 e to the power minus 3x and a constant. And to do this one, I changed it to e to the power 1/2 x because I want everybody to see that the coefficient of x is 1/2. So you divide by 1/2. So you get 1/1/2 e to the power of 1/2 x plus a constant. Now 1/1/2 is 2. Again, the reason I did that, I just want to make sure that you don't have to change this to 1/2 x if you see the coefficient is 1/2. The integral of x squared minus 7x plus 2 over x squared. We cut this into 3 fractions. Here's 1. Here's minus 7 over x. Here's 2 over x squared. So cut it into 3 fractions. To get it ready for the next step, we're going to rewrite this as the product of minus 7 and 1 over x, and this one 2x to the power minus 2. So now 1, again, the independent variable is x. 1 gives you x. Minus 7 times 1 over x. You can keep it like that. The reason I wrote it in this manner, because the integral of 1 over x is natural log. So you recognize this as a natural log. Keep the -7 intact. So minus 7 times ln of absolute value of x. What about this one? We're going to go with the power rule, everybody. You're going to use the power rule. 2 divided by -2 plus 1, x to the power of -2 plus 1, which makes it minus 2 x to the power of -1. So -2 over x and a constant. That would be the final answer. One plus cosine t dt, the integral of that. First, pay attention to the fact that the independent variable is t, so 1 gives you t. And cosine, the derivative is negative, but the integral is positive sine t and a constant. The integral of cosine is sine and a constant, so sine t and a constant. What about this? Cube root of x must be changed to x to the power of 1/3 to be ready for the power rule. So we write it as 1 over n plus 1 x to the power of n plus 1. That means 1 over 1/3 plus 1 x to the power of 1/3 plus 1. So that's the first piece. Minus The derivative of sine is cosine, but the integral of sine is negative cosine. So minus minus cosine x and a constant. Now, of course, this is plus. This one is 4/3, which makes this one 3/4, or 3/4 of cube root of x to the power of 4 plus cosine x plus a constant. Please understand, as usual, we don't have too many steps of calculus, but we do have algebra involved. Now, I want you to notice this means 2 times 1 over x. That's the reason I rewrite it. You don't have to if you see that. When you see 1 over x, of course, you see the answer. So 2 times natural log of absolute value of x plus a constant. So again, rewriting it because we can clearly see the answer as a result of that. We do the same thing here. We rewrite it as the product of 1/2 and 1 over x. So we can see the 1/2 remains, and you're working on this piece, which is again a natural log. So 1/2 ln of absolute value of x plus a constant. Let's work on this. Make up 2 fractions. This one and this one. Needless to say, the denominator is x to the power of 1/2. And again, quite a few algebraic steps to get it ready for the power rule. This one, when we don't have the exponent, is 1. 1 minus 1/2 is 1/2. So this is x to the power of 1/2. This is x to the power of negative 1/2. Now, 1, 2, 3, already 3 steps of algebra. We've done this already. 1 over 1/2 plus 1, x to the power of 1/2 plus 1. This one, 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1, and a constant. At the end, we add a constant. And believe it or not, this is the only calculus step, everybody. We're done. We have to finish off the algebra. 1/2 plus 1 is 3/2. Negative 1/2 plus 1 is 1/2. This means 1 over 3/2 makes it 2/3. This means 1 over 1/2 makes it 2. So the final answer is 2/3 x to the power of 3/2 plus 2x to the power of 1/2 plus a constant. X squared plus 2 over x squared plus secant squared. This is one function, that the one fraction. Makes it 1. This is the second fraction, 2 over x squared. And I'm going to change the 2 over x squared to 2x to the power minus 2. Again, we've done this. We are getting it ready for integration. Number 1 results in x. This one is 2 over negative 2 plus 1. If you go back to the notes, we've already done that. It becomes minus 2 x to the power minus 1, or negative 2 over x. And the integral of secant squared, tan x, and a constant. And that's the final answer. So what we have been dealing with is solving anti-differentiation or integration problem. In essence, is a differential equation. And now we want to solve an initial value problem. First, I want to explain the meaning of that. Any equation containing a derivative is called a differential equation, short DE. So what we have been doing for this section has been solving differential equation. A function which satisfies the equation is called a solution to the differential equation. Just like you're solving any type of a function, okay, a quadratic function, a rational function. So the name of the function, the name of the equation, and the name of the solution. An initial value problem is a differential equation along with a specified value of the unknown function called the initial condition. In this case, if you look at this one, it represents the pair 0, 1. And what we are going to do, for now, we're going to ignore that. And we are going to solve this as we've been doing before by putting d2. I just want you to ignore that for now. And this is dp equals the right side times dt. And if you integrate both sides, the left side is p as a function of t, and the right side must be integrated. So that's an easy case. As you know, the answer is itself divided by the coefficient of t, or 3, and a constant. What you have here is a solution which is called a general solution. What makes it general is this. So this creates a family of functions. What do we mean by that? If you graph this function, plus the c takes it along the y-axis up and down, whether it's positive or negative. For example, plus 5 takes it up by 5 units. Minus 8 takes it down by 8 units. So that's the purpose of the c. It's a general solution that we've been looking at all along so far. So what is the difference now? Now this means the pair 0, 1. And if you have a pair, now for this function p of t equals 2/3 e to the power of 3t plus c, you can plug in and find the constant. So p of 0 equals 1. So 2/3 e to the power of 3 times t, which is 0, plus the constant equals 1. E to the power of 3, 0, that means e to the power of 0, that means 1. So this is 1. So 2/3 plus what number is 1? 1/3. So we found the constant, we replace it, and now this is an initial value problem. The difference is now you have a particular solution. Meaning, this, everybody, represents infinitely many different functions, a family of functions. This is one of those functions. How did we find it? With the help of one pair. Therefore, we just solved an initial value problem. A DE, a differential equation, was just solved. Here's another example. Solve the initial value problem. dy dx is 1 over x plus 1 over square root of x. Y is 5 when x equals 1. In short, there is a pair. So first, we are going to ignore that and solve this, which means dy is the right side times dx. And then y is the integral of the right side. Or you can integrate both sides. The integral of dy becomes 1. So we are going to integrate. And that's something, again, we have done. Both pieces have been already done. We're going to go over them again. So this one, we just rewrite it as x to the power of 1/2, bring it up, make it negative 1/2 to make it ready for the power rule. Obviously, 1 over x is a natural log. Natural log, everybody. And then this one, we use the power rule. 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1, and a constant. So y equals ln of x plus 2 square root of x plus a constant, and that's a general solution. Now we use the pair 1, 5, and we find one of those solutions. So replace the y with 5, x with 1. As you know, ln 1 is 0. So this is 2 times 1 is 2, plus c. C must be 3. Replace it, and you get one of those solutions. Particular solution. So one more time. Ignore that, and you solve it as usual. Gives you a constant, which means a family of functions, a general solution, infinitely many solutions. Then the pair will help you find the constant, which means you find one of those solutions. And that's it. This is an initial value problem. Rectilinear motion. A particle moves in a straight line and has accelerated acceleration given by a of t equals 60 plus 4. Its initial velocity v of 0 is negative 6 centimeters per second. And its initial displacement is s of 0 equals 9 centimeters. Find its position function s of t. So what is the rectilinear function? By the way, the derivative of the position function is the velocity function, and the derivative of the velocity function is the acceleration. Okay, so rectilinear motion. For motion in a straight line with constant acceleration, a initial velocity v sub 0 and initial displacement s sub 0. The displacement after time is s of t equals half of a t squared plus v0 t plus s sub 0. You may remember this from physics, but we are going to discuss that here, and this can be easily proved. Okay. You just start with this, and then you end up here. The acceleration is constant at t, initial velocity, and you can integrate to come up with the answer. All right. So in this case, v prime is a of t, and it's given as 60 plus 4. So we are working our way back to the original function, namely the position function. So first, we go to the v function by integrating this. So the anti-differentiation, v of t would be the antiderivative of the 6 over 2t squared plus 4t and a constant. So we are writing the antiderivative of a of t, known as the velocity function. Now, we know that v of 0 is negative 6, so if we use it here, we can find the missing constant. V of 0 is c, or v of 0 is minus 6. Just plug in. If you plug in 0, this goes away, c becomes minus 6. And that's v of t. So one more time. Since v of 0 is negative 6, and therefore we get this. Again, notice if I change the t to 0, I get v of 0. This goes away, becomes c, and it's supposed to be negative 6. So that's the answer, and now we want to find s of t. Let's integrate this. The antiderivative of this one I hope you realize 3 divided by 3, 2 plus 1 is 3. So this gives you t cubed, this gives you 2t squared minus 60 and d. Again, what I'm doing again in essence is the following. So I'm integrating this, and it gives me this. And what I want to do, I don't want to repeat the, see, normally we use a constant and I used something else because I don't want anybody to think these two must be the same. That's why I used a different variable. And we know S of 0 is 9. So if I plug in 0 here, I get D. So D must be 9. And that's S of t. S of t is t cubed plus 2t squared minus 60 plus 9. Just to make sure everybody understands what's going on. A quick reverse process and take a look at it. If I differentiate this, t cubed gives me 3t squared, 2t squared gives me 4t, minus 60 gives me minus 6. Now if I differentiate this again, 3t squared gives me 60, 4t gives me 4. So integration. A sample of cesium-137 with an initial mass of 79 milligrams decays T years later at a rate of negative 1.8249 e to the power of negative 0.0231 T milligrams per year. Find the mass of the sample after 23 years. Round your answer to 1 decimal. The moment you see the rate in calculus, it means differentiation. So because we are interested in finding the mass, let's call it M of t. Let M of t represent the mass of cesium-137 after t years. So if that is the case, what is its derivative? dm dt, or m prime, if you will, is this rate. With the initial value m of 0 being 79, so dm dt is this, m of 0 is this. We can find m of t in general, and then plug in 23 to find m of 23. That is the process. So first we find m of t, and m of t would be the integral of this piece times dt. Class, m of t is the integral of the right side times dt. You need the dt. There is no dt or dx or anything like that. The integration is meaningless. There must be a typo in that case. And as you know, in the case of a e to the power of kx, the derivative and the integral are the same. The derivative we multiply by k, the integral we divide by k. So that's why the answer is itself. We are going to divide by the coefficient of t, negative 0.0231. We are using this. And of course, we add a constant. If you put it into a calculator, this is 79. And because m of 0 is 79, we can find the constant. So this is a general solution class. So we are looking at a DE. This is a general solution, okay? Now, replace the T with 0 to find C. M of 0 is 79. So you get 79 plus 79 e to the power of 0. As you know, e to the power of 0 is 1. So the constant becomes 0, right? Because 79 equals 79 plus what number? And so m of t has this formula. So this is a general solution. And this is a particular solution. Now, find the mass after 23 years. So plug in 23 here. When we plug in 23, right here, t is replaced with 23, put it into a calculator, you get some number, and pay attention, we want 1 decimal. So to get to 1 decimal, you need the next one. Number 3 says number 4 doesn't change, 46.4. And as always, units. This was milligrams per year for the rate, so this must be milligrams. So that's an application problem. 5.1, areas and distances, the method of exhaustion. Areas of familiar polygons, such as triangles and rectangles, enable us to find the area of a more complicated region by filling the region with increasingly smaller elements of known area. This is called the method of exhaustion. Notice, if you put a three-sided versus 4, 5, and you add to the number of sides, a triangle, a rectangle, a pentagon, and so forth, the area of that figure can be easily calculated, and it's getting closer and closer to the area of a circle. This is at the time where they didn't know the area of a circle was pi r squared. So if you want the area under the curve, you follow the same methodology. The area problems. Find the area of the region S that lies under the curve y equals f of x from A to B. This means that S is bounded by the graph of a continuous function where f of x is larger than or equal to 0. We are dealing with a positive function. The vertical lines x equals A and x equals B, and the x-axis. Now, we can write this region as follows. S equals set of pairs x comma y such that x is between A and B and y is between 0 and f of x. Remember, the x-axis has the equation y equals 0. So how do we do that? One way is to cut this into rectangular strips. For example, if you cut it into 4, and this entire interval of b minus a, the distance of b minus a, you cut it into 4 pieces or 10 pieces or n pieces. This small distance called this sub-interval delta x is b minus a over 4 in this case, or b minus a over n. So you keep the width fixed. What is the height? The height could be any point in between. For example, for the first one, you can use the left endpoint, the right endpoint, the midpoint, and so we use the Riemann sum. Summation of f of x of I delta x as I goes from 1 to n is f of x of 1 times delta x, all the way to f of x of n times delta x, where delta x is b minus a over n. Now, just so you see, again, the concept is very important. If I go with the left endpoints, means the height for the first one is this much, everybody. This is the height for the first one, which is f of a. The height for the second one would be this. For the third one, I'm using the left endpoints would be this. And for the last one would be this. So look at those points. F of those points would be the height of each rectangle. If I use the left one, if I use the right one is different now. Right one I have to use, take a look, I'm going to use a different color. Right one, this would be the first point, second, third, and fourth. If I use the midpoint, I can use the midpoint here. For example, here, this would be the rectangle. The point is, you can approximate the width. Is it the area? No, it's an approximation. And that's the idea, everybody. It's an approximation of the area. But what happens when we add to the number of strips? As we add, the approximation gets better. And that's really the concept that we should pay attention to. Suppose a continuous function f is defined on the closed interval of a to b. If the interval is divided into n subintervals, so that delta x is b minus a over n, x sub 0 is a all the way, and x sub 1 is a plus delta x all the way to x sub n, or a plus n delta x, which is b. Then a Riemann sum associated with f is the sum of f of x sub I delta x as I goes from 1 to n. X sub I is any point in that subinterval. A sub I minus 1 to a sub I. That means you could use the left, the right, the midpoint, any point. Makes no difference because none of them gives you the answer. Each one is an approximation. So having said that, here's the geometry and procedure called Riemann sum. Partition the interval of A to B into, let's say, 4 subintervals. So make 4 rectangles with delta x being b minus a over 4, and the height of f of x sub 1, f of x sub 2, f of x sub 3, and f of x sub 4. That would be the right endpoints, by the way. Make it into more, like 8 or more rectangles. What happens? As the number of rectangles increase, the approximation gets better. Now, left endpoints, right endpoints, midpoints. It has a formula, and I'll show you how to easily come up with the answer without having to memorize that in a moment. But the idea is that all of them have the subinterval delta x. Now the left endpoints, they use the left endpoints x. So they use all the points that you've cut a comma b into except b. That's why you have f of x of n minus 1 stops. For the right endpoints, they use all of them except a. That's why you don't have f of x of 0. And the midpoint is the sum of these two divided by 2. So the approximation A is almost equal to the summation of f of x sub I delta x as I goes from 1 to any number, not just 4. This is for 4. But if you let n go to infinity, it becomes the actual area. So this one, you take a limit and you let n go to infinity. The area under the curve is exactly the limit as n goes to infinity of summation of I from 1 to n, f of x sub I delta x, where delta x is b minus a over n, and x sub I is a plus I delta x. I'm going to show you how this thing works with a very simple example, everybody. It says use the LEP, left endpoints, REP, right endpoints, and midpoints rules with n equals 5 to approximate the integral of 1 to 2, 1 over x dx. So later on, we use the easy way out known as the FTC, or fundamental theorem of calculus. But basically, this is the same as the Riemann sum. And again, it's approximated by that. If you take a limit, becomes the exact answer. Okay. Now, if this represents a positive function, then it represents the area under the curve. If it's not positive, it represents difference of area. So having said that, we go back to this. We want to see what is the function. The function is y, or f of x equals 1 over x. And since it goes from 1 to 2, from a to b, a is 1, b is 2, and n is given as 5, they should give you n. So the very first thing we calculate is delta x, which is b minus a over n. Okay. And so what we are dealing with here, the graph of y equals 1 over x, everybody's familiar with it, looks like this, right? And we want to go from 1 to 2, which means we want this area. And it is not a geometric shape that we can calculate, so we are estimating it with n equals 5. And so delta x is b minus a, 2 minus 1 over n or 5, 1 over 5 or 0.2. Now, here's the method that I want to show you how you can use. See, this is the formula for left endpoints, right endpoints, midpoints. I want to show you an easy way you don't have to memorize. 1 to 2, draw a line segment from 1 to 2, make it large enough so it's easy to see. And then it starts with 1, it ends with 2, and just add 0.2, 0.2, 0.2, or 1/5. So you have the following. A is 1, everybody. B is 2. Remember, we made this large enough so it's easy to read. Then A is 1, then add the delta x becomes 1.2, 1.4, 1.6, 1.8, and ends with 2. Now, for the left endpoints, L5, so we want to find L5, and that would be basically following that formula, delta x times f of what? Here's the easy way out. When you want to use the left end points, use all of this except B, because you're using the left end points. This one, this one, this one, and this one. So you want delta x, which is 0.2, times f of 1 plus f of 1.2 plus f of 1.4 plus f of 1.6, f of 1.8. Again, don't choose the last one because you're using the left ones. So what is f of 1? Well, go back to this function. 1 over 1, 1 over 1.2, 1 over 1.4, 1 over 1.6, 1 over 1.8. And you put it into a calculator with a lot of decimals. Normally, they tell you how many decimals. Normally, it's like 6 or 7 or 8. So 0.745634920. We put a lot of this. Now, what about the right endpoints? Delta x times, now use all of them except the first one because you're using the right endpoints. So that means f of 1.2, f of 1.4, f of 1.6, f of 1.8, f of 2, but not the first one. So delta x is 1/5. See, we use 1.2, 1. So 1 over that, 1 over everything except the first one. And you come up with the answer. By the way, this part is being repeated, everybody. So this is for the sake of simplifying your calculation. Notice again, the left endpoints uses the very first one, A. The right endpoints uses the very last one, B. And so these 4 parts, because there are 5 of them, 4 of them are in common. You don't have to rewrite. Now, what about the midpoints? And again, it's an easy way of calculating. What is the midpoint? That means here. If this is 1.1, all you have to know it's 0.2. So the next one you should add 0.2, 1.3, 1.4, 1.7, 1.9, and take a look. Is an approximation. Delta x times f of 1.1 all the way to 1. So you don't have to memorize these formulas. It's very simple, everybody. And so you plug it in, you end up with this answer. And of course, midpoint is a better approximation for the area than the left as well as the right. 0.691908. So a quick recap so everybody can follow what we did. We were interested in evaluating this, and eventually we will evaluate this with FTC, fundamental theorem of calculus, which is a lot faster. However, we want to go with the Riemann sum, and if you want to go with the Riemann sum, if you want to approximate it, they have to tell you how many sub-intervals, which is n. N is 5. So you have to find delta x, which is b minus a over n. And this is the area you want. This interval of 1 to 2, a to b, you make it huge for the sake of seeing exactly what you do. Cut it into whatever n pieces is, in this case 5. Now, the width is delta x. The height for the left endpoints, use the functional value at all of these points except b. The right endpoints, use the functional value at all of this except a. So take a look. Left endpoints uses the a not b. This one uses b not a. And the midpoint, just if you come up with the first midpoint, then you add the delta x. All right. The velocity of a moving object is given by the function v of x is 3x, where x is in hours and v is in miles per hour. Use geometry to find the area under the graph, which is the distance the object has traveled during the first 3 hours. Now, v of x equals 3x. I hope you realize y equals mx goes through the origin, and it looks like that. So this represents the time in hours. This is the velocity, function of x in miles per hour. And area represents the distance. Well, the area is a triangular shape, half of base times the height. So we need to recognize this point at 3, y, or in this case, v of x is 9. So this point has coordinates 3 and 9, which means the base is 3, the height is 9. Plug in. So 1/2 times 3 times 9 is 27 halves, or 13.5 miles. We want to find the distance between the third and the fifth. So this is what we want. There are 2 ways to do that, class. We can calculate the total area from 0 to 5 in the same manner that we did here, and then subtract 0 to 3. And 0 to 3, we already have that. You can do it that way. Or this is a trapezoid, and the area is 1/2 the height times base 1 plus base 2. And if you treat this as a trapezoid, the height is this much, 5 minus 3. So the height is this, everybody. 5 minus 3, or 2. Base 1, we have one of them is this distance, which again, remember this was 9. And one of them is this, which is 6 and 9, 15. If you want to go that route, of course, these two cancel each other. So the answer is 24 miles. As I mentioned, you can also find the total area here and subtract this much from it. Either way is fine, whatever is easier for you. Use the definition to find an expression for the area under the graph of f as a limit. Do not evaluate the limit. F of x is x squared plus the square root of 1 plus 2x, and x is between 4 and 7. Find delta x and x of x. First, again, reminding you the area under the curve is exactly as follows. The limit as n approaches infinity of summation of I going from 1 to n f of x of I delta x. We will evaluate this limit later on, but for now, just want to set it up. So A is 4, B is 7, and delta x is b minus a over n, which makes it 7 minus 4 over n, or 3 over n. So this is A, this is B. In other words, they may give you in this format or in this format. Makes no difference. X sub I is A plus I delta x. So A is 4, I delta x is 3 over n. 4 plus 3i over n. So we have everything. Now we're going to move towards this limit where it says A, the area is the limit of, and if this is the using the right endpoints, R represents the right, Rn as n approaches infinity, the limit of summation of I going from 1 to n as n goes to infinity of f of x of I delta x. So we have x of I and we have f of x. So we write x of I is 4 plus 3i over n, and f of x is this function x squared plus the square root of 1 plus 2x. So we are going to replace each x with this expression. So replace it here and here. So f of x of I would be, this one would be 4 plus 3i over n to the power of 2 plus the square root of 1 plus 2 times this expression. So this is f of x of I. What is this limit? You put this into a limit. The limit as n goes to infinity, summation I going from 1 to n of f of x of I. You write this one times delta x. Replace it with 3 over n. So you write A is the limit as n approaches infinity of summation of I going from 1 to n. Parentheses, brackets 4 plus 3i over n squared plus the square root of 1 plus 2 times 4 plus 3i over n, and the entire thing times 3 over n. This is the limit that eventually we will evaluate. And we'll see it's pretty complicated. And it becomes easier when we use FTC, Fundamental Theorem of Calculus. But for now, we want to be able to set this up. So we got this limit, and of course, later on, we evaluate. Determine a region whose area is equal to the given limit. Do not evaluate the limit. Again, we are not evaluating the limit as n approaches infinity of summation of I going from 1 to n of 3 over n squared of 1 plus 3i over n. In other words, you want to find the function and you want to find the limits a to b. Okay, and so again, here's the equation for the area, this limit. Here's delta x, b minus a over n. Here's x sub I, here's delta x. And again, we're using the right endpoint. So let's rewrite this one where we compare, and we can see that since delta x is b minus a over n, and it gets multiplied by f of x of I, there seems to be that delta x is 3 over n. And this is f of x of I. So delta x is 3 over n, and f of x of I is this expression, square root of 1 plus 3i over n. Let's work on this. We know delta x is b minus a over n, and we know x of I is a plus I delta x. And we know, so we just write the information from here. Okay, so this piece, this is this, okay? And now, what is delta x? 3 over n. What is a plus I delta x? So let's write this. This is 3 over n. This is 1 plus 3i over n. A plus I delta x, right? We know that delta x is b minus a over n, so b minus a must be 3. B minus a must be 3. If this is a plus I delta x, and this is delta x, this is I delta x, then a must be 1. And if a is 1, what happens here? B becomes 4. So I hope you see the step-by-step justification as to how we arrive at each part. So the function seems to be y equals f of x over square root of x from 1 to 4. So take a look at this one. Y equals f of x equals square root of x on the interval of 1 to 4. And by the way, you can work it out and get to this, just the way we did in the previous example. Imagine this is given. You can easily get to this following this again. So number 18, the function was given, and we wanted to get to this part. Number 19, this is given, and we want to get to the function, and of course, the interval. So you really want to visit the two questions simultaneously, 18 and 19. So one goes from the function and the interval to the limit. One from the limit can figure out the function. However, the function is not always unique. For example, we know delta x is 3 over n. So what if we said a is 0? What if in case we do that? If we say 0 plus I delta x, which makes it 3i over delta x, 3i over n. So a becomes 0. If a is 0, b must be 3. And if that's the case, the function is 1 plus x instead of just x under the radical. So this function, y equals f of x equals square root of x, and the interval of 1 to 4 is the same as y equals f of x equals square root of 1 plus x on the interval of 0 to 3. That works the same way. So it may not be a unique function. Another way of calculating this, an application of that, finding the area, approximating the area, is here by finding the answer here for this velocity. The velocity graph of a car accelerating from a rest to a speed of 120 kilometers per hour over a period of 30 seconds. So it takes 30 seconds to get to that speed is shown. Estimate the distance traveled during this period, the first 30 seconds. So the area under the curve, estimate the distance traveled during this period, and they're asking us to use m, the midpoint, m sub 6, to get the best estimate. Okay, it's better than the right endpoints and the left endpoints. Round your answer to 3 decimals. Again, reminding you of the area which is approximated by the Riemann sum. And because we use the midpoint, we say delta x times f of x of 1 bar, this bar meaning the average between the left and right side. And so what is happening here? We are going to cut this into 6 equal pieces. Okay, so we want, so this is the area we want, and we are going to approximate it with the methodology of the midpoint. So delta x is b minus a over n. So b minus a over n. That means 30 minus 0 over how many pieces? 6 pieces. 5. So 5 what? If this is 30 seconds, each subinterval is 5 seconds. Now, because we want to approximate this, and the units are kilometers per hour here versus seconds, you either have to go with hours here. Remember, 1 hour is 3,600 seconds, or you have to change this. One of them has to be done. So 1 hour is 3,600 seconds. You want to estimate the distance, remember that. So delta t, which is 5 seconds, is how many hours? 5 seconds divided by 3,600. And it becomes 1 over 720 hours. Again, this part, because we have to go with the same units class, kilometers per hour, this is in seconds. That's the reason. All right, so the interval of 0 to 30, we want to cut it into 6 pieces. So A is 0, B is 30. 5, 10, 15, 20, 25, 30. We are going to use the midpoints. So first, let's do the drawing. These are the, so we have 6 rectangles. And we are going to use the midpoints. So to use the midpoints, those are the midpoints, everybody. Which is obviously 2.5 here. And then add 7.5 and the rest of them. So this is the formula for the midpoint. And again, I don't see any reason to memorize it. It's delta x, which we already have. In this case, delta t. Okay, so we have delta x in general. Delta t is 5 seconds, which we are not going to use 5 seconds. We are going to use 1 over 720 hours because this is kilometers per hour. So then the velocity at 2.5, 7.5, add 5, 12.5, 17.5, 22.5, 27.5. So those are the midpoints, everybody. Look at the midpoints. You draw those lines. So you want this area plus this area and so forth. That's the idea. So what is, for example, just for the sake of argument, the first one, that would be this width, which is fixed. Delta t is 1 over 720 h times this height. And this height, you do the reading. Now, the heights are the velocity of 2.5, as I mentioned here, 7.5, and then I mentioned that you add 5, 12.5, 17.5, 22.5, 27.5. So you have to do the reading. Now, this reading may not be easy to do for this one, but the one that you come across, it'll be easy to read. So you try to read the best, and the numbers that you read for 2.5, for example, or 7.5 and so on, or 31.25. These are the readings from the graph. This number, this one, this number, this one, this number. And you add them up, divide by 720, you get 0.725. And now, because this is in hours, this cancels this one, and the units will be in kilometers. So for the first 30 seconds, it covers how much? 0.725 kilometers.